Folks, welcome to CS10 Lecture 21, Saving the World from Computing. Woo! So exciting. So exciting. I'm really delighted to have my good friend and colleague Kathy Yelick here today to give you this talk. Kathy's by day, she's an ECS professor, normal, amazing faculty member in our department. But by other day, she has these two jobs. It's incredible that she's doing this. She is the Associate Lab Director for Computing Sciences and the Acting NERSC Directory of Lawrence Berkeley National Labs. This is a big deal, folks. It's not like that. That is a massive research facility up at the top of the hill that has hundreds, not that thousands, hundreds?
4,000.
4,000 employees, and she is the director.
3,000.
That's amazing. Okay, so we have a really power hitter today, and there's nobody I could think of better to give this lecture. Kathy's been so generous with her time to give this to other CS10 classes in the past, and this is always the highlight of many people's CS10 career. So, folks, let's give Kathy a hand for coming to CS10. Woo!
Great. Oh, I'm very excited to be here. This is actually the highlight of my semester since I'm not teaching regularly in my day job as an ECS professor anymore. I get to come and give this lecture once a semester. So it is one of the most fun things I do. And it's always great, though, that Dan introduces me to some new and interesting technology. So we're going to try the new and interesting technology here and hope that everything happens. There's a little green light on. Is that a good... There. Is it good? It's good. Okay. All right. So yes, I'm going to talk today about all the great things you can do with computers, including a lot of things that we do up at Lawrence Berkeley Lab. By the way, we'd like to emphasize the Berkeley Lab part of Lawrence Berkeley National Lab because, contrary to popular opinion, Lawrence Berkeley National Lab is not in Livermore, it's in Berkeley. So just if you walk straight up the hill or Hearst Avenue, keep going past Foothill Housing, and then you kind of wiggle around to the left, you'll see Lawrence Berkeley National Lab, and that's where we're building a new computer facility up there. It's going to be very exciting. So I'm going to talk about using computers for science and engineering. So why do we use computers in science and engineering? Well, we use them because we have problems that are too big, like you're trying to understand the origins of the universe, and it is too big to just go out and measure the universe. Although we do that, we measure all the little pixels that we can see from here to try to understand what happened right after the Big Bang. You can actually see a blueprint sort of that in the sky. So things that are too small, so really tiny things. I'll talk about molecules, proteins, things like that. Things that move really fast, things that move really slow, and things that are either too expensive or too dangerous to do. So this is all of the cool things you can do with science. I was actually at a meeting a few weeks ago with a bunch of people from industry, and somebody from Procter & Gamble gave a great talk. It's online, by the way. I can give Dan a pointer to it later if you want to see things that are not really, you might not think of as science and engineering. It has to do with how you design products. So this is more of an engineering problem, and computers, believe it or not, in fact, including some of the fastest supercomputers, are used for things like designing diapers, designing toilet paper, designing the processes, the machines that you manufacture them by. So think about this. Toilet paper, what do you want the properties of toilet paper? Well, you want it to be soft, but you want it to be strong because you're going to produce it at 40 miles an hour, and as it flies off of the conveyor belt, so it can't fall apart until you want it to. It has to be perforated in certain ways that are just perforated enough that it tears when you want it to, but not when it doesn't. And they use computer simulations to figure that out. They use computer simulations to make diapers feel good to babies, but not feel good for toddlers, so they stop using them. All kinds of great things like that. They're used in science for understanding diseases, for developing energy-efficient devices, and there's industrial products that looks like soap bubbles there. So we call simulation and computing the third pillar of science. What does this mean? So my kids are still middle school, early high school. They're learning about science. So when you start learning about science, you do things like you learn physics, right? You roll these cars down planes. You measure how long it takes for them to get down a certain ramp of a certain height and distance and so on, and learn about F equals ma. What's F equals ma? That's a theory. A theory says, well, we think that this is the way that mass and acceleration and forces are related. So that's a theory, and then we can run experiments like rolling these cars and stuff like that, and you do these experiments. Well, what do you use simulation for? What you do is you basically implement the theory. So you plug in F and M, for example, and get a bunch of accelerations out, or you can plug in the other two variables and get the third one out. And you can build much more complicated systems in which you're applying F equals ma to something like simulating the forces on diapers. And so you use the computers then for much more complicated systems to try to tie together the things you're seeing from experiments and the things that you believe to be true based on the theories that you've developed from earlier experiments. So I'll talk about two of the biggest problems that are facing the world today and how we use computers to try to address those kinds of problems. And those two problems, you can just kind of think of what are the world's biggest problems. Well, there are a number of them that you might want to address, but two of the big ones are the changing world around us, that is the environment, climate change, understanding how the world is changing, and what are things that we can do to try to reverse climate change. The second category is health and medicine. What can we do to try to understand the disease mechanisms and develop better treatments and drugs and things like that. So there's a couple of projects, actually several projects up at Berkeley Lab that have to do with the first of these problems, which is understanding climate change and understanding what we can do about that problem. The overall project here is called Carbon Cycle 2.0. The name Carbon Cycle 2.0 means how can we develop a new sustainable carbon cycle? That is, it may not look exactly like the carbon cycle existed pre-humans, that is before we started with all these forcing functions of the greenhouse gases, but can we get back to another stable cycle in which we're actually kind of recirculating and recycling the carbon that's being produced? And there's a whole set of different research problems in the picture of developing a new carbon cycle with climate change and understanding climate impacts there in the middle. And all around the outside are things to develop new energy efficient devices and buildings to have, these are combustion engines looking at ways of capturing carbon and sequestering it underground, developing alternative fuels, solar PVs and things like that. So there's a whole bunch of pieces of the picture, and if you listen to the Secretary of Energy, Steve Chu, who actually used to be in the physics department here at Berkeley and also was the director of Lawrence Berkeley National Lab, he will say that the solution to the energy problem and the global climate change is not a single one of these things. It's not like biofuels. If we create biofuels, that will solve the problem. It has to be a whole set of things. So we're going to use computing to try to understand that. These images are taken from simulations done at my center that's called NERSC, the National Energy Research Scientific Computing Center. And these are all simulations that are used to try to help address these different parts of the carbon cycle. So I'm going to start by talking a little bit about climate change and this movie. So this is simulating the hurricane season. This is research done by a couple of Berkeley Lab scientists, one who's an expert in computer graphics and visualization, and one who is an expert on global climate change. This is data that's been run by a lot of different researchers around the country to simulate these hurricanes. And what you see here looks almost like a movie of the climate, but what you're seeing there is actually these different hurricanes that are forming, and these are from computer simulations or computer models of what the climate looks like in a particular season, a particular hurricane season. So how do you build a program like this to simulate climate change and to simulate things like these hurricanes? Well, what you do is you take the Earth and you build a data structure that's going to represent the Earth. Basically, you're going to divide the Earth up into little tiny pieces and and each one of those is going to simulate what's going on in that part of the Earth, which will keep track of things like what is the temperature, is the sun shining at this particular part of the simulation, how does that heat things up, what does it mean, what does it do to the wind dynamics, does it create wind because of a difference in temperature between this part of the world and something nearby, and so on. And so a couple of different data structures. There's actually a big debate right now about what's the best data structure for doing this kind of climate change. So even in this high energy, sort of big science area, people don't really agree on what the data structures are. So the one at the top there is called the cube sphere. It's like you take a cube with little boxes all around it and you kind of squash it until it's round and it turns into a sphere. The bottom one looks like a soccer ball with little tiny hexahedron for the pieces of the soccer ball. So there's a couple different things that people are debating about. But that's what these computer simulations look like. Now, a question actually a good question I got the very first time I gave this lecture in CS10 was, how do you know that you're getting anything reasonable out of these simulations that you're doing? And the answer is it's a very good question, and we spend a lot of time doing what's called validation and trying to understand whether we have built a model that is a theory and implemented it correctly in our computer software in order to get a correct simulation. This is data that Gil Campo from the University of Colorado has put together, and he's actually built a big database that's available to all of the science community. And what you see on the left-hand side, so how do you validate something like a climate model because the climate changes too slowly? Well, you can wait 100 years and see whether the predictions that the models told you were going to happen actually do happen. But of course, we don't really want to wait 100 years to see if all of these if the climate warms and the sea levels rise and all these other kinds of things happen. So instead they go back 100 years and then simulate forward starting 100 years ago. Where do you get climate data that's 100 years old? Well, there's not a lot of it, and the little red dots that you see on the left-hand side are actual measurements from back about 100 years ago that they were able to collect. So this is not quite 100 years ago. 1938 was a hurricane, although they actually go back even further in their database. And they collect the data points together that come from ships in the ocean, from naval measurements. They come from newspaper reports in little cities that have collected climate data and things like that. And then they run a bunch of very sophisticated algorithms on top of them to try to smooth out the data and fill in all the missing pieces. And they collect this data then that is three-dimensional data, and they can tell you what the climate was like every 6 hours for 100 years, going back in time. And then they take this data and they run it forward in time. You'll see this is actually a hurricane that was hitting New York in 1938. On the left-hand side is the actual data, on the right-hand side is the simulation, and you can see that although they don't look exactly the same, you can see that the hurricane actually does look very similar to the actual data. Now, you can get really depressed looking at all the information about global climate change, but there is good news in it, and we use computers to try to understand how we can do things to reverse climate change. Question here addressed by Warren Washington and a number of other scientists is, can global warming impacts be diminished if we actually significantly cut greenhouse gas emissions? And in this simulation on the bottom, we're looking at a 70% decrease in greenhouse gases. At the top, we're looking at business as usual, where we would continue to produce more and more greenhouse gases. And the answer is yes, there's a significant difference between the top and the bottom pictures. On the top, actually, the temperature raises by over 3 degrees Celsius. And the bottom, it rises by, it still goes up, but it rises by less than 2 degrees Celsius in most of the populated areas if we can cut the emissions by 70%. It turns out also some of the most significant impacts in the ocean circulation do not happen in the bottom simulations. And so there are things that can be reversed if we can take into account these, we can take advantage of various mitigations. Now, we use simulations also to try to change the climate problem by developing things like new energy efficient devices. This is looking at a flame from a combustion engine. There's actually an experimentalist at the lab and a mathematician at the lab that work together. John Bell is the mathematician in his group, and Robert Cheng is the experimentalist. Robert Cheng has developed these things called low swirl burners, and you can tell that it's an energy efficient burner because it's not wasting any heat out the sides, and that's why he's got his hands wrapped around it with no gloves or anything, is because it's a very cool burner, but the heat is all coming out the top where you want it to be. And you can design these things in little tiny burners that fit in your hand that you could use in something like a dryer or even smaller device, and you can have industrial scale burners, which is that big huge one there, and they use these for developing heat for a number of different kinds of applications. But they'd like to understand how you can use, say, things like biofuels or other fuels that don't produce so much carbon in them, and that's where the mathematicians come in with their simulations. And this is a simulation that tells them something about the details of the combustion process and exactly how to design these burners to make them both as energy efficient as possible and also make it possible to use other kinds of fuels. Another example of an energy efficient device is looking at how you store energy, and this is actually turning sunlight into thermal energy, into heat, so storing it as heat that you can release later. And this is a little video, we'll see if this works, from Jeff Grossman, who actually used to be at UC Berkeley and is now on the faculty at MIT.
Spinning around here. And what it can do is it can store energy from the sun internally and release that energy later as heat on demand. It works in some ways like a rechargeable battery. It can be charged and reused many times over. In this case, the charging occurs simply by exposure to sunlight. So when the sun strikes this molecule, it undergoes a reaction that transforms it into a higher energy state, or a charged state. And this particular molecule is a special case. It can do this reaction in a reversible manner with no degradation. That means that once transformed by the sun, it stays stable, making it safe and transportable. Then, using a simple catalyst, the molecule can be made to go back into its original state. And as it goes back into its original state, it releases that stored energy as heat. And this makes it essentially a rechargeable heat battery. What we wanted to know is why this particular case is unique, why it's so stable and does not degrade over time, unlike other molecules that have been tried before. So we carried out quantum mechanical calculations in order to understand the heat release mechanism. And what we found was quite surprising. As the molecule proceeds along the reaction pathway from the higher energy state back to the original state, it was thought to have only a single barrier. But the calculations revealed the presence of this intermediate state, which means it has two barriers along the pathway instead of one. And that has important implications for how the fuel is stabilized. And what we find is that the relative barrier heights along this path play a crucial role in its functionality. Using this knowledge, we're now working to develop further improvements in the fuel, such as the use of cheaper materials and also increased storage densities.
In some cases, though, we're still going to be burning coal. We're going to be doing things that produce carbon. And so the last application here in this area is looking at how we can actually get rid of the CO2 that we produce. This is a process called carbon capture and sequestration, or in this case, sequestration. And it's looking how you can capture the carbon produced, for example, out of a coal burning factory and then pump it underground and store it there so that it doesn't impact the rest of the environment. And these are some simulations that have been done by researchers, once again, at the lab, looking at these kind of, what happens when you try to sequester carbon. Okay, so those are many of the applications of computing applied to this kind of environmental problem, the global climate change problem, and how to do something to fix it. I'm going to talk next about the other big application area, which is really looking at health and medicine. So here I'm going to ask you to think kind of long-term about a 20-year vision. This has been a 20-year vision, by the way, for about 10 years, so it kind of keeps rolling forward. But we think we're actually making some progress on it. And imagine that you have a digital body double. That is, you have a digital record of all of your images from any kind of medical records, any medical tests that you've done, pathology, information about your diagnostics, and also information about whatever medications you're taking and things like that. And you can use this for diagnosis. You can use this for less invasive surgery. If they actually understand exactly what your internal organs look like, they can design better prosthetic devices, and they can understand how to do surgery with robots. So the digital human today is mostly about imaging, and there are some of these particular simulation problems. There's a great project online. How many people have ever looked at the Visible Human project? Just a couple. All right, well, I'll show you a little bit of it. The Visible Human Project is this online database. It's used a lot in, I think, in teaching medicine, but it's used in a number of other applications in trying to understand the structure of the human body. What they did is they took two cadavers, a male and a female, and they were frozen, sort of sliced very thin, if you will, and imaged each one of those slices. So there's 18,000 sections of the body. The male was sectioned was done first, so it was lower resolution, 1 millimeter sections, and the female was done a little bit later at 0.3 millimeter sections. And it was there are a number of applications of it, and a number of different people that licensed this. So I'm going to show you a little movie from the Visible Human Project. You can find this movie online as well. We are now flying through the human body. This is an actual human body that you're going through. You're now obviously in the legs, and you're going to hit the feet here in a minute. And so you can see that there's all this data that shows exactly what the human body, these particular two cadavers, look like online. So that's the first problem. That's kind of when I talked about where do you get the data for climate modeling, this is the question of where do you get the data for doing something like a simulation of the human body. You have to start with some very detailed images or other kinds of information. Now this is specific to one person. The question is, can you build some sort of general model so that we don't have to slice you up in order to build a model for each one of you that's more specialized. A number of years ago, I worked on a project that was heart simulation, and these are actually visualizations that come from a group at NYU that we were working with at the time. This is actually a PhD student who worked on this project a little later, but he had great movies, so I decided to use his movie rather than ours. This is showing a simulation of the human heart and how the blood flows within the heart. And what you can see here, and this is a little bit easier to see with the muscle fibers, and you can see the blood going up and down between the different, these are the ventricles, is all you're seeing here, the atria are up above, and there's the blood, the oxygenated blood coming down in red, and the deoxygenated blood there in blue. So this is something that you actually can be used to understand things like artificial heart valves, even artificial hearts, how to design these kinds of devices to make them very efficient. It was used at one point to try to understand how to treat infants, newborns that have a particular kind of heart defect. So in this heart defect, their heart is not really wired correctly, and so they're in danger of not getting enough oxygen. And what they do in these is because the infants are too small and sort of unstable to sustain a major surgery like rewiring, recabling their heart, what they do first is they go in and they make a little hole in the walls of the heart so that just a little bit of the oxygenated blood mixes into the deoxygenated side, which is just enough to keep the baby kind of growing well enough that they can get a little bit stronger so they can do the major surgery. And the question is, what was the optimal size and shape for that little hole to be? And they use computer simulations to understand that. Hearts are just one part of the body. There are a number of other researchers who have looked at other parts of the body and computer simulations of them, trying to understand how the lungs work, and of course what you'd like to do then is tie the heart and the lungs together to understand how the oxygen comes from the lungs and goes into the blood system. How does this affect the kidneys? And there's the heart itself is very complicated. It has electrocardiography, which is what causes the muscles themselves to contract. And then it has the blood flow, which is the part that I was showing you before. The blood pushes on the walls of the heart, and the walls of the heart push back on the blood. And one more example of a simulation is looking at how diseases what causes diseases and how we can create various kinds of drug treatments for these diseases. There's a project at the University of Washington by Valerie Daggett called Dynamiomics. Dynamiomics is looking at these proteins, but instead of just looking at a protein and its structure, you're actually looking at the movie of how this protein folds, or actually the simulations are done how the proteins unfold. So she ran, at our nurse center, she ran 11,000 of these protein unfoldings for a related set of what are called amyloids, these proteins that are actually behind the cause of Alzheimer's and mad cow disease and other neurological diseases. And using this, they're able to understand something about the common patterns with these different proteins and in the way in which they fold. So it's not really that the structure of the protein is different, it's that the way in which they fold and unfold is different between the good ones and the diseased one, and that helps them also then to design drugs. And so that's another application of using computers to understand things about medicine and health. And the last one here, I've just put a little piece of a New York Times article that I recommend reading. There's a whole series of these about using computers to solve a number of different problems. This is our own Dave Patterson, who is also on the faculty in the Computer Science Division, looking at how you use computers to understand cancer and develop treatments for cancer. And this is called the Big D applied to the Big C. So Big D is big data, and big C, of course, is cancer, and saying that computer scientists have a lot of what it may take in order to really try to figure out how to solve this big data analysis problem. So this one's not so much of a simulation problem, it's looking at lots of data that comes from genomics databases. There's a database that is at another UC school, I believe that's at Santa Cruz, that they're looking at that has all of this cancer data, genome data in it. Okay. So, why study computer science? This is not a voting one. This is just because computer science can help us solve important problems. Hopefully, I gave you some ideas of how we can solve important problems with computer science. The second thing is the second reason to study computer science is because computer programming is fun, and there are still a lot of new problems to solve. So you may think that, you know, computer science is kind of an established old career by now. Haven't we figured out all those computer science problems and there's nothing left to do? So let me talk a little bit about some of the really cool problems in computing. I'm going to give you, I was at this meeting that I mentioned before, and I want to talk about a couple of sort of major breakthroughs in computing and think about what this means about computing performance, because that slide was really about computing performance. So Jeanette Wang, who used to be the head of the computer science program at NSF, is now on the faculty at CMU, where she's been. She gave a talk at the beginning of this meeting talking about, you know, how do we use computing today? So you wake up in the morning, and the first thing you do is you use your iPhone. And I said, before you even get out of bed, right? And I said, no way. And then I looked using Google, and I looked and said, it turns out they've done a study, and it says that 30% of people use their iPhone in the morning before they ever get out of bed. So, okay, there you are with your iPhone, looking at something, maybe searching Google. So the next thing you do, this is what I do when I'm on travel. I got my iPhone there for my alarm clock, and I look to say, where is the closest Starbucks so that I can go get some coffee? Okay, so these are called black swans because they were unanticipated things in computer science that changed the field and changed the world. We did not know that iPhones were going to exist or that Google was going to exist, but they, you know, so if you roll back 20 years ago. So how important was all this stuff about Moore's law and computing performance and those kinds of black swans? Well, if you go back 20 years into 1992, and you say everybody came up with all these great ideas, they had all the ideas behind the iPhone, they had all the ideas behind Google, what happens? Well, your iPhone is, that's actually a computer that was at NERSC at the time. NERSC was located at Livermore. It's a Cray YMP. It was their new scaled down model, supercomputer from Cray, and it weighed only a couple of tons. And so you've now got a couple of tons sitting on your bed with you when you wake up to access your iPhone. You go to Google. So how does Google work? Well, Google's data centers today use about 20 megawatts of power. But back in 1992, they would have used at least 20 gigawatts of power. Okay, so now Google, we all know this, Google's a green company. They really want to push green. So where can you get 20 gigawatts of power? Anybody know where you can get 20 gigawatts of green power? Water. Okay, but who knows where that is? Where can you get a hydro gigawatt power plant? China, somebody said. That's right, Three Gorges Dam in China. So now you got no network, by the way, that can get you with high speed to Google if you want to download images. So you have to fly to China, go to the Google data center there, do your Google search right there at Three Gorges Dam, and now you can get the information that you want out of Google. So the point of this is not that it's just that in order to make these kinds of things happen, you needed to have computers that got much faster, much smaller, much cheaper, and much more energy efficient over the last 20 years. Or all of the great ideas that we've had in computing would not have happened, or many of them would not have happened. And so going forward, we can say, well, Google's kind of fast enough the way it is. My iPhone's kind of fast enough the way it is. What you don't know is 20 years from now, what will not happen if we can't make computers go 1,000 times or even 1,000,000 times faster than they are today, which is what happened 20 years ago. Okay, so this is mostly kind of a reference slide in case you're not familiar with all the terms, but there's, these are all the different terms for how big computers can be and also how big memory can be. So starting with kilo and then up to where are we at today? We're at petaflops in terms of the size of our systems. Petabyte store, so that the cancer data that I talked about, 2 petabytes sitting in this database for researchers to access. The fastest computer we have today at NERSC is a petaflop system. We're all trying to figure out if we can build an exaflop system, because like I said, we don't know what will happen if we can build an exaflop system, but we figured good things will happen with computing, so we're trying to do that. And this is a history of the fastest scientific applications in the world, and the pictures of the computers on which they were run over about the last 20 years. And there's a prize that's given out by Gordon Bell every year at a conference called Supercomputing for the fastest computers in the world. I mean, the fastest applications, so some kind of computer simulation running on these computers. And so back here at the beginning, you can see pictures of those vector supercomputers, those Cray computers. There were also NEC and other companies that were building these vector supercomputers. What happened in the early 90s was somebody gave a talk on Attack of the Killer Micros, and this is where people started building networks of workstations, and we called it the NOW project here at Berkeley. Clusters is the more popular phrase, so this is where we started taking microprocessors of the same kind that are in your laptops and were in servers at the time, and then just connecting these things together into a big cluster. So that really changed the nature of this kind of high-performance computing from these specialized vector supercomputers to these clusters. 2004, something really important happened, which is processor manufacturers stopped figuring out how to make processors go any faster even though they had more transistors on the chip. But because they had more transistors on the chip, they started just putting multiple cores on the chip. So now when you go out and buy your laptop, you get a Core 2 Duo. So I think you've heard about that a little bit in this class already. But so the rest of the world kind of woke up to parallel computing. There's our projected, hopefully, exascale computer in 2020. It's actually, if we believe the trend, it would be in 2018, but I don't think we're probably going to get there in 2018. And so what is the big transition that's going to happen to help us get from where we are today? We're not going to make the processors go any faster because they're too hot. So instead, we're looking at something like Attack of the Killer Cell Phone. So what does this mean? The big problem in trying to build a computer that is 1,000 times faster is energy. And that's true whether you're trying to build a cell phone that's 1,000 times faster or you're trying to build a supercomputer that's 1,000 times faster. Our supercomputers, for example, might be about 100 cabinets, so 100 refrigerator-sized boxes in the machine room. And we don't want to make that 1,000 times bigger. And we don't want it to use 1,000 times more power. But the real problem here in building this is going to be energy. And cell phones, if you want to go out and talk to somebody who knows how to design an energy-efficient computer processor, you talk to cell phone designers. I thought that cell phones were limited by battery life, right? Because you want it to last all day long. But in talking to one of them, they said it's actually the first thing that you do worry about battery life, but the first thing you worry about is how hot it is, because people really do not like to walk around with hot cell phones in their pocket. So that's why you talk to the cell phone designers. This is a picture of Hopper, which is our petascale supercomputer. And just to give you an idea, that has it's got 150,000 processor cores. Each one of these is an AMD chips inside of those. Each one of those chips has 12 cores, a Magni-Core processor. And now imagine you're doing one of these climate simulations. You've got this data structure with all these little pieces in it. It kind of maps onto a parallel machine pretty easily, because you take each one of those little icosahedral meshes cells, and you put it on each one of the processors. And then they have to talk to each other in the middle of the simulation to say, hey, the temperature went up here, so it must have gone up over there, or whatever other physical aspects are happening. And that's true with a lot of all of the different physical simulations. Most of them are done with these kinds of what's called domain decomposition. You divide up the domain and you give each domain to each processor. So now programming these things is a hard and interesting problem. The machine, as I mentioned, is named after Grace Murray Hopper, and Grace Murray Hopper is known for a few things, but one of which was to popularize the phrase bug. So a picture right there is of the very first computer bug. The very first computer bug was a physical bug. It was a moth in the computer that caused the computer to not work. And Grace Murray Hopper was the one who kind of made everybody start using this word for any time the computer didn't do what you wanted to do. We call it a computer bug. She also, by the way, designed COBOL, the COBOL programming language, and was one of the kind of pioneers of programming languages in computers. So energy is the big problem with trying to make computers faster, no matter what scale you're at. This was a project I was involved in, looking at how many megawatts a computer would use if we tried to build one. And this usual scaling means take into consideration Moore's law scaling. With Moore's law, the wires get shorter, so it doesn't take as much energy to move the data around. The transistors get smaller and so on. But even with Moore's law scaling, which are those step functions, we still got up to a design point for an exaflop computer of about 200 megawatts. So how much is 200 megawatts, for those of you who are not so used to paying electricity bills at your home or at your university because somebody else does it for you? It costs $1 million roughly per megawatt per year to run one of to buy electricity. Prices vary across the country and so on, but roughly speaking, think of it as $1 million. So that means to run one of these exaflop computers would require $200 million just to pay the electrical bill every year. So we're not going to do that. So we are trying to figure out how to at least shrink that down by a factor of about a factor of 10. The Hopper system today is about a 3 megawatt computer, so I spend about $3 million a year, a little less because we get good pricing, but every year paying the electrical bill for Hopper. And this isn't just a problem with supercomputers, it's a problem for security. So the NSA had problems because they're browning out all of Baltimore when they turn their computers on. Google says, you know, there's an article that Google details and defends its use of electricity. So they're using about 260 megawatts, so about a quarter of a gigawatt in all of their data centers. I'm kind of guessing they have about a dozen of them, which is where I came up with the 20 megawatt number per data center. And worldwide, the data center power was about 26 gigawatts, so $26 billion spent powering up these data centers. So energy is a big problem here in computing. And so if you go into computer science, you can help solve these problems. There's the cell phone processor, and there is this is an Intel Nehalem processor, so a high-end server processor. The server processor is 100 times faster, 1,000 times faster than the cell phone processor, but is the server processor is 10 times faster than the cell phone processor, but it uses 1,000 times more power, so it's actually less efficient. The cell phone processor is 100 times more energy efficient in terms of the number of operations it can do per watt. So this has to do with some basic physics and the way these devices work, which I won't go into, but if you've taken your double E courses, it's V squared F, and it all turns, you have to raise the power when you raise the frequency, and so that's why these little tiny lightweight processors that are very simple and have slower, or a little bit slower, are actually much more energy efficient. So the big question for us is, are we going to build our next supercomputers out of graphics processors? Fastest supercomputer in the world in China, built out of graphics processors today. There's another one being installed at Oak Ridge National Labs, which will also have graphics processors in it. Game processors, a few years ago, the fastest supercomputer in the world, one of the first petaflop systems, was built out of cell processors. So those are PS3 processors built into a supercomputer, or are we going to build it out of something like cell phones? So lots of interesting questions there. How are we going to program the thing, and so on. So as I mentioned before, all of the processors today now, it's not just a problem for supercomputing. They're all these parallel processors, and there's our Moore's Law line, just to prove to you that really the trend in Moore's Law is continuing. But the processor performance is the red one. That was what leveled off in around 2004, and instead this green line is about number of cores per chip, so we're getting a lot more cores per chip rather than getting faster processors. I was in another study group with a number of people looking at computing performance with the National Academies. Sam Fuller, who is the chair of that group, put together this nice graph that kind of summarizes the previous picture and says this is the expectation gap between where everybody is used to Moore's Law producing not just more transistors, but actually producing more computing performance, because the architects figured out how to turn those transistors into faster and faster computers. And it allowed you to have more memory, it allowed you to have more, it allowed you to have bigger data sets, bigger operating systems, and allowed you to do a lot more things. So this is the kind of, most computer science don't think about this particular part of the problem because they're off designing algorithms and thinking about great things to do with computers, but that's the expectation gap where things will not happen that we're kind of expecting them to. Dave Liddell, who's actually a venture capitalist, works in the venture capital industry, had this great analogy to the computer industry having to do with what happens when you fly jet engines, and he said that the planes, and he said that there's these two different speeds that you care about when you're flying a jet. One of them is the maximum speed at which you can safely fly at all. So don't exceed that because you can't fly safely. But the other one is called maneuvering speed. So maneuvering speed is where you can fly in a straight line, but you can't turn because you're going so fast that you can't actually change course at all. And he said the computer industry was running at maneuvering speed, which means we figured out that Intel x86, AMD, and so on, processors were the way to do it, so we just made them faster and faster, and we could keep doing that. And then something major happened, which was 2004, they got too hot, and the computer industry couldn't really turn. So all I could do was to say, oh, we know what we'll do. We've got more transistors. We'll just stick 2 of them on the chip. Now we'll stick 4 of them on the chip, and so on. And so the computer industry has to make a major change here. So the last kind of reason to study computer science is because there's a lot of great things that you can do with computers that are fun to do in addition to all these science problems. I will just mention briefly the computer music. So you may not think that if you're a musician that you can benefit from computers, but David Wessel, who works at the Center for New Music and Audio Technology, he created this loudspeaker array. He's also a practicing musician, a performing musician. He's built a musical instrument out of the track pads from a bunch of computer systems. So I think he's got a 5x5 grid of those, each one connected to a different sound or voice, and he uses that to play music. So computers get used in industry, and to my surprise, he said musicians have an insatiable appetite for more computer power. And the last thing I'll show is a little video from the graphics group from James O'Brien here at Berkeley. And I just want to show this. This is looking at computer games. Many of you may recognize this. My 13-year-old son certainly does. This is Star Wars Force Unleashed. And so just a little bit of this, and then I'll try to... So this is of course an interactive game. Those of you who don't play games, they might not be so familiar with it. And let me see if I can move it here a little bit. There we go. So these are now, what I want you to see is the mesh that they're putting. So how do you simulate these things? Well, what are you doing in a game? You're simulating the physical world. When you're simulating the physical world, you're building these models, and they're built out of these things that kind of look like these, that looks kind of like the world, the mesh. These are finite elements, and indeed that's exactly what's going on both with the people and with the brick wall. So there's a brick wall and people flying into the brick wall. This is what happens now if we change the physical characteristics, the theory of that brick wall, and make it rubber instead. And so it's, you can see you get very different behavior. So I'll just end with a quote from E.O. Lawrence, who is the founder of Lawrence Berkeley National Lab. Computational science is necessarily collaborative. You have all these great people working together to solve, who are experts in physics and chemistry and medicine, in biology and climate change, and you get them together with computer scientists and mathematicians, and that's what he said in his Nobel laureate acceptance speech as well. So why study computer science? For all the reasons I said before, plus you get to work with a bunch of great people in a lot of different disciplines.